make a quick comment on the answer we got for the previous problem. So if you didn't do this problem in detail, go back to the previous video. If you have a conductor in electrostatic equilibrium in the shape of a sphere, we showed that the electric field is zero inside the conductor, and outside it's like the electric field due to a point charge. And we showed that the potential outside is the potential due to a point charge, and inside it just continues with the value at the surface all the way into zero, to r equal to 0. But remember, when we talk about potential, you can always add a constant to the potential. I mean, this particular choice of the answer was based on the choice that the reference of potential is 0 at infinity. That's why when you put here r goes to infinity, you get 0. So this is a particular choice, but you don't have to make this particular choice. You could choose any reference, the reference to be 0 anywhere you like. If you want to consider the potential to be 0 inside the conductor, you can do that. And you can do that by shifting the whole potential curve downwards by a constant amount. So if you shift the potential downwards by constant amount equal to kq over big R, then outside, in the region outside of the conductor, the potential would be kq over R, what we had before, minus this constant amount. And this would what the potential would look like. Here, in the region outside, when you let R goes to infinity, what will you get? You'll get minus kq over R. So this asymptotically goes to minus kq over R at infinity. So in this problem, in this way of solving the problem, the potential at infinity is not taken to be 0, it's taken to be a constant amount. This is a perfectly valid solution. Remember that the electric field, when you get the electric field from the potential, you take a derivative with respect to position. And so when you take a derivative, this constant goes out and you get exactly the same electric field that you would if you considered the potential to be kq over R only outside. So you can always shift the potential everywhere, at every point in space. You can always shift it up and down as you like, depending on where you want the reference of potential to be. So to summarize this problem, if someone asks the question, what is the potential inside the conductor, you first need to determine where the 0 of potential is. Once the reference is determined, then you can find the potential at any other point. But remember, the electric field has to be the same no matter what choice you make for the potential reference, because the electric field is the force per unit charge on a test charge that we place at some point in space. And the force is something you can measure in the lab. So this has to be the same always, no matter what the choice of potential is.